All right, so in this section, we're going to be talking about sampling distributions and the central limit theorem. I've kind of alluded to the central limit theorem a couple of times over the last few months, but today we're going to specifically talk about what that tells us. Okay, so sampling distribution. The definition says a sampling distribution is the probability distribution of a sample statistic that is formed when random samples of a certain size are repeatedly taken from a population. So what this is saying is that if we were to take, so let's say we were to take a sample of 12 people, and we were continually to take samples of 12 people, this is what's going to end up happening, okay? So basically, it's just taking a whole bunch of samples with the same number of people and seeing what happens to with those number of samples. So we're going to take the average, and we're going to find the standard deviation and stuff like that. Okay, so if a sample statistic is the sample mean, then this distribution is the sampling distribution of the sample means. Every sample statistic has a sample distribution. Okay, so we're going to talk about what that means here in just a little bit, but let's go ahead and illustrate this. Okay, so let's go ahead and pretend like this box represents the population average. Okay, and let's say that these little circles represent a sample. Okay, so we take a sample, and then we take another sample, and we keep taking samples from the population to see what the distribution looks like. Okay, so we take all these samples are the same size, and we're just kind of looking to see what they look like. Now, some of these samples could overlap, so maybe I sampled the same person, but it really shouldn't matter. Okay, so some properties of the sampling distributions of sample means is that the average, so the population average, so the average of all of these samples, okay, so the average of all of the sample averages, okay, this is how we denote it. So mu with a subscript x bar is equal to the population average, okay? So this says the average or the mean of the sample means is the population mean. Okay, so the mean of all the sample means is the population mean. Okay, so we're using this to find the sample distribution or the sampling distributions. Okay, the other thing we're going to have to be able to calculate is the standard deviation of all of the sample means. Okay, so the standard deviation of the sample means is simply the standard deviation of the population divided by the square root of n, or the number of samples. Okay, so again, the standard deviation of the sample means is equal to sigma divided by the square root of n. All right. The standard deviation of the sampling mean is called the error of the mean, or the standard error of the mean, and we're going to talk about that later on in the later chapters. Okay, so the standard deviation of the sample means is called the standard error of the mean. Okay. All right. So example number 1, it says list all possible sizes n equals 3 with replacement for the population 1, 3, and 5. Then we're going to calculate the mean of each set, or each sample, and then we're going to find the mean, variance, and standard deviation of the means. Okay, so this does take a little bit of work, so I will be doing this with you guys in class on either Monday or Wednesday so that we can kind of go over this stuff. Okay, so we're going to kind of skip over example 1. We'll do this in class. You could actually go into the book and read that example if you'd like to get ahead. All right, but we're going to go ahead and move on into the central limit theorem. All right, so we're going to break this down into 2 parts. So first of all, if a random sample of size n, where n is greater than 30, okay, so we're taking sample sizes of n where n is greater than 30. And this refers to any population with a mean mu and a standard deviation sigma. Then the sampling distribution of the sample means approximates a normal distribution. Okay, so if your sample size is greater than or equal to 30 in any population with an average and a standard deviation, then we can go ahead and approximate the sample means with a normal distribution. Okay, so let's go ahead and illustrate what this means. Okay, so this is number one, the population distribution. Okay, so a population distribution typically doesn't always look like a bell curve. Okay, so oftentimes it may look something like this. Maybe it's kind of some really funky type of graph where it doesn't really follow that bell shape. Okay, and so maybe the average of the population is somewhere in here, right? So remember, to use a standard normal distribution or normal distribution, the average has to be at the peak of our data set. Okay, so we've got our mean, and maybe this represents the standard deviation. So the standard deviation here is the distance from the mean. Okay, so what we can do, or what happens, is if n is greater than 30, or greater than or equal to 30, our sample size is greater than or equal to 30, we can actually normalize this. Okay, so we can take a whole bunch of samples from this population, right? So we can just take a whole bunch of samples from this population, and what ends up happening is it creates a bell-shaped curve, okay? Where the center here is the average of our averages, and then our standard deviation is the standard deviation of our averages. Okay, so we take the average sample, or the averages of each sample, and we're going to average those out to find our new bell-shaped curve. Okay, so this is a way of normalizing our curves. All right. So part 2 says that, well, what if we have a random sample size of n where n is any sample size? So in this case, remember, this is n has to be strictly greater than 30. Okay, so this now is talking about where it's any sample size n. Okay, so the only way that this can happen is if it's specifically stated that the population is normally distributed. Okay, so the only way that this works is if the population is normally distributed. So when I draw this picture, this is a normal population distribution, right? So a normal population distribution is a bell curve. So we have a bell curve here. Okay, so as long as we have this bell curve, then we know that that any sample that we take should be normally distributed. Okay, so this would be our population average and our population standard deviation. So if we were to take this, so any n, okay, all it's going to do is, so if we are taking averages as samples, our standard deviation actually does get steeper or smaller. Okay, so our curve is going to be a little bit steeper here. Okay, so we still have our average, right? So our average of the sample means is equal to the average of the population. The standard deviation, again, the standard deviation will be a little bit closer. So the standard deviation of the population mean is equal to the standard deviation of the sample means is equal to a standard deviation divided by the square root of n. Okay. So let's go ahead and take this information and let's apply it to some examples. All right, so by looking at this, it's a little difficult to tell whether this is a bell curve. So remember, a bell curve should follow this. That was a horrible line. It should follow something like this, okay? So we don't have a bell curve here. Let's go ahead and read it. And it says, a study analyzes the sleep habits of college students. The study found that the mean sleep time was 6.8 hours. So that's one of those things that we're going to need to pull out. So the mean sleep time was 6.8 hours with a standard deviation of 1.4 hours. The random sample size, so a sample size was 64, there were 64 sleep times that we pulled from the population. We want to find the mean and the standard deviation of the sample means, and then we're going to sketch a graph and compare it with the sampling distribution. All right. So first of all, because our n is greater than or equal to 30, we can indeed use a normal distribution, okay? So we know that the population mean is 6.8 hours, and we know that the population standard deviation is 1.4 hours, okay? So to calculate the population, the mean of all of the sample means, well, it's simply going to be 6.8. Okay, there's no calculations as long as it's normal distribution. Okay, the standard deviation though does require just a little bit. So the standard deviation of the population means is going to be 1.4 divided by the square root of whatever our n is. So n, remember, is 64. Okay, so we're going to take the square root of 64. All right, and when we do this, we get 0.175. Okay, so there's our standard deviation. All right, so we want to go ahead and draw this. Okay, so I'm going to draw it down at the bottom left, right down here. Okay, so we have our line. So I am leaving some space over here in this area so that we can interpret these results here in just a second. So I do want you guys to leave that space empty. All right, so we know that our average is 6.8, and we know that a standard deviation is 0.175. Okay, so 0.175 would be right around 7 here, and we'll go ahead and we'll just make it 0.2 up and down, so 6.6. Okay, so we have our average. Okay, I like to go ahead and put some points here so that we have these. Remember that the first standard deviation is going to be your inflection point. Okay, so it opens downwards. It's a parabola opening downward through the first standard deviations, and then it's a parabola opening upward after that. Okay, so it's a parabola opening upward on the outside of those two standard deviations. All right. So here we are. This should be 7 over here. All right, so we have our distribution. Okay. So now we want to go ahead and we want to interpret. Okay, so from here on out, I'm going to be expecting you guys to interpret your results anytime you come up with a result. Okay, so we can say that from, go ahead and zoom in, from the central limit theorem, so I'm going to label this as CLT, because the sample is greater than 30, the sample distribution can be approximated by a normal distribution with a mean of 6.8, and so this is just where we're going to write our results of 6.8, and a standard deviation of 0.175. Okay, so again, we're just going to kind of tell us whether we can actually normalize this, okay? And then at the last part, we're going to state what the results of that normalization is. So that's what the goal of this is. All right, so the next one. So notice, just by looking at this, notice that we already have a bell curve. So it should state somewhere in this that we have a normal distribution. Okay, so it says the diameter of fully grown white oak trees are normally distributed with a mean of 3.5 and a standard deviation of 0.2 feet. Random sample sizes of 16 are drawn from the population, and the mean of each sample is determined. We want to find the mean of the we want to find the mean and standard deviation of the sampling distribution of the sample means, and then we're going to sketch a graph. So we're going to do similar to what we did up here. Okay, so first thing you always need to figure out is whether this is normally distributed, right? So that it was stated in our setup. Okay, we know that the mean of the population is 3.5 feet, and we know the standard deviation of the population is 0.2 feet. Okay, and we know that n is 16. Okay, so because it said it was normally distributed, we don't care what the population size or the sample size is, because it will always be normally distributed. All right. So let's go ahead and do a little bit of work. So first of all, let's calculate the sample or the mean of the sample means. Okay, so the average sample mean, right? So the average sample mean is always just going to be the population average. Okay. Then if we're calculating the standard deviation of all of our sample means, it's going to be 0.2 divided by the square root of 16, which gives us 0.1. Okay, so we have our distribution of the sample mean. So as we take more and more samples, this is what the curve should look like. Okay. So, if I were to draw this, okay, we have our average in the middle, so 3.5 feet, and our standard deviation of 0.1. So I'm actually just going to subtract 0.1. So 3.4, we'll do 3.6 over here. Remember that these are your inflection points. Okay, so it curves downward between these two inflection points, and it curves upward on the outside of them. And there we have it. We have our mean and our standard deviations. All right. So now we need to go ahead and interpret this. So interpretation. Okay. So again, from the CLT, or the central limit theorem, because it was stated the population is normally distributed, the the sample will be normally distributed. With a mean of 3.5 and a standard deviation, or an error of 0.1. And again, we're going to talk about errors much more in this class in the following chapters. All right, so let's go ahead and take a look at this first example where we're actually working some stuff out. All right. So one thing I want you to recall is that to calculate the z-score is simply the value minus the average divided by the standard deviation. And you can actually apply this to the central limit theorem, okay? So it'd be the value, or the average of your sample minus the mean of the samples, the mean of the average of the samples divided by the standard deviation of the mean of the mean of the sample. Okay, so it says the figure to the right shows the mean distances traveled by drivers each day. You randomly select 100 drivers ages 16 to 19. What is the probability that the mean distance traveled is between 19.4 and 22.5 miles? Okay, now this is made easier if you use your calculator and you actually go into the second VAR's, the normal CDF function that I showed you guys in class. If you don't have that available to you, I'm going to show you how to do this by hand. If you do, you can skip to the end and just kind of look at the results and the interpretation. All right, so the first thing we need to check is our sample size greater than 30, or does it state that it's a normal distribution? So it does not state that it's normal distribution. However, our sample size is greater than 30, so we can go ahead and move on with this. Okay, we know that our average of our sample size, or sorry, the average of the population, ages 16 to 19, drives around 20.7 miles. So I'm going to go ahead and put the average is 20.7 miles. Okay, with a standard deviation, and it gives it to us at the end, the standard deviation of 6.5 miles. Okay, so we want to first start by calculating what the average of the samples are, the average of the sample averages. And this is simply going to be 20.7. There's no calculation to do with that. Okay. However, the standard deviation of the sample averages is going to be 6.5 divided by the square root of n, which is 100. Calculating this is 0.65. Okay. All right. So again, just assuming that we don't have, that we're having to do this by hand, okay, the first thing you're going to want to do is to calculate your z-scores. Okay, so z, we'll do it down here. Z of the first one is going to be the first limit, so 19.4. So 19.4 minus the average, so 20.7, divided by the standard deviation, so 6.5. Okay, we calculate this, and it comes out to be about, or actually it's exactly -2. Okay, calculating the second z-score, same way. So this time we're using 22.5, and you get approximately 2.77. Okay. So doing this by hand, it does make it a little bit more difficult, but we can still do it. So it's going to be the probability of x being between 19.4 and 22.5. This is the same as saying that we want the probability, so we can use our z tables at this point. -2 less than x less than 2.77. Now, sorry, it's not x, it's z. Okay. Now, when we're doing this...
Hey, teachers, this is the final call. If anybody wants to come to a COVID test with the nurse, she's going to be here till 11. Thank you.
Sorry. When you're doing this, remember you have to calculate the upper area first. Okay, so we're going to find the probability that z is less than 2.77, and we're going to subtract the probability. So we're looking at between, so we're going to subtract the probability that z is less than -2. Okay, so doing this will give us, if you're checking your z-scores, your z table, you get 0.9972 minus 0.0228. Again, you're just kind of checking through your information or your Z tables that are on in your book. And then we get a probability of 0.9744. All right. So remember, we do need to interpret this. So this is the probability, right? We do need to interpret this probability, okay? So of all samples on drivers ages 16 to 19, of size 30, or size 100, approximately 97.4% of the means sorry guys. Approximately 97.4% of the means will be hold on guys, sorry. Okay, so sorry. Sorry, 97.4% will drive between 19.4 and 22.5 miles an hour, or miles per day. Okay. Okay. All right. So example number 5. We're just going to keep moving. I'm going to skip through this and kind of assume that we're using calculators here. So again, when you're using your calculators, you simply need to plot in your X values instead of putting Z values. So there's no reason you need to be converting these unless you're doing them 100% by hand. All right. Okay, so it says the average sales price of a single-family home in the U.S. is $235,500. You randomly select 12 family houses. What is the probability that the mean sales price is more than $225,000? We're going to assume that the sales price is normally distributed. All right. So what we're looking for is the probability that our sales price is greater than $225,000. Okay. So we need a couple of things here. The first thing we need is the average. Okay, so the average of our of the houses in the U.S. are $235,000, $500. Okay, and then the standard deviation of our population is, we're going to assume $50,000. Okay. Now this says it's normally distributed, so we can actually find the mean of the sample means, which is, again, it's just the same. We don't have to do any real work here. And then the standard deviation of the sample mean is going to be equal to, let's see, that would be 50,000 divided by the square root of 12, which I got approximately 14,433.76. So this would be the standard deviation of the sample mean, so the sample error. All right. So the next thing we're going to do is we're going to calculate the probability using this. Okay, so again, you're going to use the normal CDF, and we're going to fill that information in. Okay, so using normal CDF, we get a probability of 0.756. Okay, so we do need to interpret this. Okay, so interpretation. The interpretation is where we're going to start getting more and more involved. So this says about 75.6% of samples with n equal to 12 will have a mean less, or sorry, I guess we're looking greater than, greater than 225,000 and about 24.4% will be at most 22,500 or 225,000. Okay, so this is the interpretation that we're going to be looking for. All right, so we're summarizing our results. The second part isn't super necessary. Okay, so as long as you have this first part, we're all good. The second part is useful when presenting it to the class. So whenever we start doing our presentations and start working through this information, I would like to have both sides of this. All right. Number 6. All right, so this is the last example we're going to do. Okay, so it says a consumer analyst claims that the prices of LCD computer monitors are normally distributed. Okay, so our claim is that it's normally distributed, so we can use the central limit theorem here with a mean of $190 and a standard deviation of $48. We want to find the probability that that a randomly selected computer monitor costs less than $200. And then you're going to, so I guess let's go ahead and start that. So we want to find the probability if we pick just a random computer monitor from our population that it would cost less than $200. Okay, so again, we can do this by normal CDF. And when you calculate this, you get approximately 0.583. Okay, so this is the probability of just selecting any random computer monitor. Okay, and having it less than $200. All right, then we randomly select 10 LCD monitors. So this is where we're going to start using the central limit theorem. So we're selecting 10 LCD computer monitors. We want to find the probability that their mean cost is less than $200. Okay, so we want to find the probability here, again, that it costs less than $200. So what we need to do from here is we need to figure out what the mean of the sample means are. Okay, so again, this is assuming that we're picking 10 over and over and over again. So we're averaging up the sample averages. Okay, so the average of the sample averages should be, because they're normally distributed, $190. And then the standard deviation of the sample averages is going to be 48 divided by the square root of 10, which you should have, I believe it comes out to about 15.2. Okay, and again, calculating this, you get 0.743. Okay, so we get two very different outcomes here. Okay, the probability of selecting any, this is the probability of selecting any one computer out of the population. This is the average if you select 10. Okay, so we're assuming we're looking for what the average is if we select 10. So this would actually be X bar. Apologize. Okay. And again, we're going to cover this a little bit more in depth in class. All right, so it then asks us to compare. So because we're comparing, we're going to be interpreting the results. Okay, so we always want to look at interpretation. So the interpretation for this, we could say, although, I guess I'll say while the probability of selecting an LCD monitor that costs less than $200 is about 58.3%. There is actually a 74.5% chance that the mean cost, or the average cost of the LCD monitors in a sample of 10 is less than $200. Okay, so again, just to kind of go back over this, while the probability, so this is looking at the first one, okay, so while the probability of selecting an LCD monitor, so any random LCD monitor from the population is 53%, that costs less than $200 is 53%. When we actually take a whole bunch of samples, we find that the probability that we get that average is about 74.5%. Okay, so the probability that our average cost is less than $200 is about 74.5%. All right. So we'll talk about this a little bit more in class, but for right now, we're going to go ahead and leave that